Hi everybody, today we are going to discuss chemical vapor deposition technique. Chemical vapor deposition technique is a coating method used to produce thin films and coatings of very high quality. Gaseous reactants are usually used in this process. In CVD, we transport one or more volatile precursors to the reaction chamber. The volatile precursors usually decompose on a heated substrate surface. This process creates some chemical byproducts as well, which are emitted from the reaction chamber alongside the unreacted volatile precursors. A lot of materials are deposited via the chemical vapor deposition method, including silicides, metal oxides, sulfides, and in this slide, there is the layout of chemical vapor deposition chamber, and you can see that from the left side, this is the entry for the reactant gases. Whatsoever the reactants we have, if the reactants are already in the gaseous state, it's okay. Otherwise, if the reactants are in liquid state, then these reactants are preheated to convert them into a gas stream. These reactants in the gaseous form come into the reaction chamber, and these reactants are adsorbed on the surface of the substrate. And after their adsorption on the surface of the substrate, these reactants react with each other to give us the product, and the product in case of CVD is in the form of a thin film. And during this reaction, if any byproducts are produced, these byproducts, along with the unused reactant gases, go out through this opening. For example, here is an example that a salt MCl2 reacts with hydrogen to give us the nanoparticles of metal, and plus 2 HCl molecules are released as a byproduct. So MCl2 mean we may take any salt with dicationic metal ion, and we can react with hydrogen, and this reaction, basically this is not a gas phase reaction. Basically this reaction takes place at the surface of the substrate. Here are some examples of uh, the reactants, the reactions which give us the products in case of chemical vapor deposition technique. SiHCl3 uh, gives us silicon plus chlorine as well as HCl as byproduct. Similarly, SiH4 affords us silicon thin film, and two hydrogen molecules are emitted as byproduct during this reaction. So these above reactions take place at a temperature range of 600 to 650 degrees centigrade and a pressure range of 25 to 150 Pascal, and yield a growth rate between 10 and 20 nanometer per minute. It means the deposition of the layers is 10 to 20 nanometer per minute. Similarly, SiH4 reacts with oxygen and it gives us SiO2 thin films, and two hydrogen molecules are released as a byproduct. Similarly, SiCl2H2 reacts with N2O and it gives us SiO2, and nitrogen and hydrogen chloride are released as byproducts. Similarly, silicon tetraethoxide is decomposed on the surface of the substrate and it gives us SiO2 and some byproducts. Types of CVD reactors. Basically, there are two types of CVD reactors: hot-walled reactors and cold-walled reactors. Very first, we will discuss hot-walled reactors. Hot-walled reactors are less commonly used compared to other types. They involve heating both the substrates and the reactor walls. So in case of hot wall reactors, at the same time, both the walls of the reactors as well as substrate is heated simultaneously. So there are certain advantages which are associated with the hot wall reactors. For example, large batches of substrates can be produced at once. Hot wall reactors are easy to operate. There is a uniform substrate temperature, hence there is a uniform coating thickness. So in case of hot walled reactors, the substrate temperature is uniform, and when the substrate temperature is uniform, we obtain thin films of very uniform thickness. Hot walled reactors can operate at a wide range of temperatures and pressures. There are some disadvantages of hot walled reactors as well. It requires a very high temperature and energy. So in case of energy input, this process is little bit costly. Coating occurs not only on the substrate but also on the reactor walls. This makes it difficult to clean the reactor. So in case of hot wall reactors, the overall reactor is heated and as a result, coating process takes place on the substrate and also on the walls of the container or reactor. So when the substrate is deposited on the walls of the reactor, this gives a loss of the product and as well this makes difficult to clean the reactor to carry out the next reactions. In case of hot water reactors, also gas phase reactions are likely to occur. The next type is cold wall reactors. Cold wall reactors are the most commonly used type of CVD reactor. They heat the substrate while cooling the reactor walls. So in case of cold wall reactors, only the substrate is heated while the walls of the reactor are not heated. This creates a higher temperature on the substrate compared to the walls. So there is a temperature gradient between the substrate and the walls of the reactor. The substrate is hard while the walls of the reactor are comparatively cold. Cold walled reactors are particularly suitable for semiconductors CVD processes. There are certain advantages associated with the cold walled reactors. For example, there are fewer coatings on the walls, making cleaning easier. Cold walled reactors require less temperature and energy. Cold walled reactors cool chemical vapor deposition processes that involve plasmas. So in case of cold walled reactors, we can use plasmas as a heating source as well. Depositions occur at a faster rate. It means in case of cold wall reactors, we may obtain thin films in a shorter time. Gas phase reactions are less likely to occur because in case of cold wall reactors only the substrate is heated, so gas phase reactions are not occurring and only the reaction occur on the surface of the substrates. There are some disadvantages of the cold wall reactors as well. For example, they are more difficult to operate, fewer substances can be worked on at once, the substrate temperature is not uniform, and coating thickness is usually not uniform. So this is a main disadvantage of the CVD reactor, cold wall reactor, that the substrate temperature is not uniform, and when there will be less uniformity of the substrate temperature, then we will not be able to get the coatings or thin films with very uniform thickness. There are some other uh, types of chemical vapor deposition processes as well, depending upon the heating source. For example, plasma enhanced chemical vapor deposition PECVD. So PECVD is a specialized form of chemical vapor deposition. The reactive gases are ionized into plasma using a combination of radio frequency or direct discharge. So the radio frequency or direct discharge current is used to ionize the gases into a plasma. This ionization process occurs within the space between two electrodes where the gases are introduced and transformed into plasma. This technique enhances the deposition process by allowing the thin films to be deposited at lower temperature. So, using plasma technique, the thin films could be deposited at comparatively lower temperatures. Another type is thermal chemical vapor deposition. In thermal CVD, coatings are easily deposited on the substrates in the open atmosphere. In this process, the precursor material is added to burning gas, making the precursor highly reactive. Deposition of thin films directly onto substrates at atmospheric pressure is possible in case of thermal chemical vapor deposition method. The precursors take heat energy from the hot gases and form efficient and uniform coating. Another type is hot filament chemical vapor deposition HFCVD. HFCVD, also known as catalytic chemical vapor deposition method, and this method utilizes a heated filament to decompose precursor gases. The hot filament serves as a catalyst, significantly enhancing the breakdown of the gases. So in this process, the hot filament is used, and this hot filament acts as a catalyst to break down the gases, and the reaction proceeds with the breakdown of the gases or reactants. Hard filament is positioned above the substrate, which is maintained at a lower temperature compared to the filament. So there is a temperature gradient between filament and substrate. The filament is more heated and substrate is at lower temperature as compared to filament. This method ensures efficient deposition of materials onto the substrate. The differential temperature between the hot filament and the cooler substrate facilitates a controlled deposition environment, leading to uniform and high quality coatings. So, the temperature gradient between the hard filament and comparatively cooler substrate facilitates a controlled deposition environment, and this controlled deposition environment gives us uh, coatings and films of very high quality. Another type is metal organic chemical vapor deposition MOCVD. MOCVD is a specialized technique extensively used for depositing single or polycrystalline thin films. Unlike molecular beam epitaxy, which involves physical deposition to grow crystals, MOCVD operates through chemical reactions. So in case of metal organic chemical vapor deposition, actually the chemical reactions takes place. In this process, precursors such as germane, phosphine, and ammonia are typically used. These chemical compounds undergo decomposition under controlled conditions, leading to the formation of thin film materials on substrates. So, during this process, actually, chemical compounds are decomposed, and during their decomposition, the thin films materials are produced and are deposited on the substrate surface. MOCVD is helpful for facilitating complex chemical transformations essential for the production of advanced material coatings. Another type is laser chemical vapor deposition LCVD. LCVD is a precise method commonly utilized for spot coating applications, especially in the semiconductor industry. So LCVD is a technique which is most commonly used in semiconductor industry. This technique employs a focused laser beam to selectively heat specific areas of a substrate. So in this technique, not all the substrate is heated at the same time, but uh, with the use of laser beam focusing, specific parts or specific areas of the substrate are heated. The localized heating by the laser accelerates the deposition process on the heated areas, allowing for rapid and controlled growth of material coatings. So, due to the use of laser, only specific areas are heated, and as a result, the development of coatings or thin films is on the specific areas of the substrate. This targeted approach ensures high precision in coating placement and thickness, making LCVD ideal for applications requiring meticulous material deposition on on complex substrate geometries. So LCVD technique could be used to deposit the thin films on the on those substrates, on those objects which have complex geometries, and this technique is uh, suitable and sufficiently gives us good results in case of objects having complex substrate geometries. Now, the benefits of CVD chemical vapor deposition is a widely used method for applying thin films to surfaces, and its popularity stems from several key advantages that make it suitable for various industrial applications. Here are some expanded insights into the benefits of using CVD. Very first, affordability. CVD is recognized for being a cost-effective coating method compared to other deposition techniques. For example, if we are going to deposit the thin films of silicon carbide, one method is that we take the silicon carbide and just heat and convert into the vapors and then collect the vapors on a substrate to get the thin films of silicon carbide. But for this purpose, we need very high temperature. At the same time, using chemical vapor deposition technique, we can deposit the thin films of silicon carbide at a comparatively lower temperature. So, based on this fact, we may say that CVD is a technique which is more affordable, more economic, more economic and affordable as compared to the other relevant techniques. Its efficiency and ability to operate at scale reduce overall manufacturing costs, making it an economically viable option for both high volume production and specialized applications where cost containment is a crucial factor. Versatility. One of the standout features of CVD is its versatility. This method is capable of depositing a wide range of materials including metals, ceramics, and polymers onto virtually any substrate. This flexibility makes it invaluable in industries ranging from aerospace to electronics, where it is used for depositing everything from protective coatings to conductive layers. So this is a versatile technique and it has broad range of applications including aerospace, electronics and several other industries, and this technique is used for developing for placing protective as well as conductive coatings on surfaces. High deposition rate. CVD processes are particularly noted for their high deposition rates, enabling rapid coating of substrates, which is a significant advantage in mass production settings. So, CVD method has a high deposition rate, and it means that by using CVD technique, we can develop the coatings and thin films in a shorter span of time. Uniform coating, the ability to provide a consistent uniform coating over the entire surface of a substrate, including complex geometries and varying scales, is another benefit of CVD. So using CVD, uh, we can put uniform coatings on those objects which have very complex geometries. This uniformity is critical in applications where the precise thickness of a coating influences the performance or durability of the end products, such as in semiconductor manufacturing or protective coatings in aerospace components. So the uniform uh, coating development by using CVD is quite helpful for specific applications. For example, for the manufacturing of semiconductor parts as well as for the development of thin films on aerospace components. High purity chemical vapor deposited materials are typically of very high purity as the process involves the deposition of vapor phase precursors that can be carefully controlled and purified before use. So basically, the reactants come into the reaction chamber in the form of vapors, and any solid um, impurity which was the part of the reactants remained behind, and only the purified vapors come into the reaction chamber. This results in coating free from impurities that could compromise the structural integrity or functioning of the coating. So impurities are left behind. As a result, we get good quality coatings. Non-line of sight deposition. Unlike line of sight processes, CVD can coat complex shapes and internal surfaces that are not directly exposed to the source of the deposition material. So using CVD processes, we can even develop films on the inside of the materials, and those objects may have complex shapes. This capability is particularly important for components with intricate designs or internal cavities that require consistent coverage, such as parts used in fluid flow systems or complex electronic devices. So, simply speaking, the parts which are used in fluid flow systems are in complex electronic devices. Sometimes it is required to put coatings or thin films on their complex internal designs, and this task could easily be done by using chemical vapor deposition. Now the applications of chemical vapor deposition method. CVD processes are used by many industries such as the aircraft and automotive industries. This technique is used to modify the surfaces to promote adhesion process. Through the CVD process, coatings increase the longevity of materials such as making metals resistant to rust and corrosion. So using CVD process, many times the industries put coatings on cutting tools, and these cutting tools are used for longer time, and the coatings afforded by chemical vapor deposition protect these cutting tools from the process of rusting and corrosion during their use. CVD is used in the semiconductor industry to make materials that are used to produce solar panels, light emitting diodes, LEDs, and integrated circuits found in devices such as cell phones and televisions. CVD also helps prepare single crystal metal oxides such as sapphire and ferrites. Lastly, it is through the CVD process that net shaped products such as tubes and crucibles are produced. The substrate is removed and leaves a freestanding thin film materials. So these are the few applications of chemical vapor deposition techniques. And I hope this video is quite informative for you. Please share this video to your friends and colleagues. And also please subscribe the channel. And I hope that in comments section you will give your valuable comments. Thank you.